now we have some understand of this group, right? We have FP star, and the element in FP star is totally p minus 1, right? And we have extension of FP, and the FP extension star has p squared minus 1 elements. And we have some inner structure under the structure. But yeah, it's I just think it's a good explain to understand the circle star. But I'm going to talk the paper literally. The paper, this thing is written in lemma 1. Lemma 1 in the circle star. Its sides, if I have a curve like this one, and I just want to, I have an isomorphic between this curve and a projective space P1. And the paper gives the map between these two things. And I just want to try to explain why, how we can find a map or isomorphism between these two things. I think it will help you to understand why. I just want to give you some high-level idea. The first one is this is a curve in the affine space, and this is I don't know, as a thing in the projective space. So I just want to give another thing. This one. I mean, this is another curve in the projective space. So I'm going to show there is an isomorphism between this one and another isomorphism between this one. So I think the paper is okay.
I think the curve on the first line is the curve on the projective space. Sorry, on the affine space.
Yeah.
Right? So the plane.
Yeah.
And the second is on the three-dimensional things.
Yeah.
Right.
Yeah.
It's just not in the same space.
Yeah. Okay. So that is why I think if we can find this, if we can understand the isomorphism between these two things directly, but we can find another easier way to build the connection. And first, I just want to recall some basic background of affine space and projective space. And so I have some notes. Okay, so we have a affine space that is like this one. And just make it direct. Okay. So we have a span space. The element in this, we have a affine space. The element in the space is just the point x and y. Yeah, and we just assume x. Okay. And we have another space called projective space. It's basically three coordinates in a point, and defining the FP. Okay, and there are some properties of the projective space, and I will think of I will just list of them quickly. And first one is we have we can multiply with the lambda. H lambda. We have the first properties. We think of these two form of point is and there is an equivalence between these two point, and we think they are the same point. Okay, and so. Another thing in the project space is we don't have all 0 points. And yeah, and this last one is I think this is this is another thing, and we can show it. We can talk about it with two cases. The first case is when z is equal to 1, and we have this one. And the second case is when z equals to 0, and we have this space. And we can see this case is exactly the affine space of n dimension, and this case is another project space with lower dimension. Okay, I just show the properties of the affine space to make us find the isomorphism between these things. So first, I'm going to show this affine space curve is there is a isomorphism between the affine space curve and the projective space curve, and it's very easy. We just apply this rule. Okay, so I just write this here. And 1 z is equal to 1, we got x squared plus y squared is equal to 1. And 1 z is equal to 0, we got x squared plus y squared equals 0. We want to this equation, we can find some solution. It's just x equals 0 and y equals 0. But you know, x, y, z all equal 0 is not exist in the project space. So that is isomorphism between this projective space, the projective curve, and the affine space curve. Okay. And now we're gonna show why this. I think P1 and this equation is in the same space now, and we can show the relation between them. Okay. Right here. Okay. First, we just want to give some intuition between the. We can find the isomorphism. We have two sides, right? Set A and set B. How to find the isomorphism between these two sides? We can find a map from set A, let's call pi, and we'll find another map from set B to set A, we call per C. And the phi and the per C have some relationship, like phi per C x equals x, and per C phi x equals x. If we can find the phi and per C, we can find the isomorphism between two sides. Right? So I will give the phi directly, but there indeed have some other forms of phi, and I just take an example. And this this example will consistent with the circle stack paper. Okay, phi is x, y, z, 2 x plus z, y. Yeah, we can find this thing as phi. But there are some bad thing is, remember we don't have 0, 0, and 0. But this map actually map to like this one. 1, 0, minus 1, map to 0, 1, 0. So this map is bad, and we can't use directly. But in the other point, the map is good. So we can adjust the map because the property 1. We can multiply some same equation to its different coordinate, and it will be the same same point. Okay, so what we gonna do is we multiply this. We just right here. We multiply this one. And we can show the first part of the point. We can show this one. Okay, it exactly we can apply the equation of this curve because the point is exactly in the curve, right? So we can apply it just minus y squared, and we keep this. Okay. Right. And yeah. And we can clear the common component of both stick point, and we can get this and this one. So this point is not 0, 0 because if you put the point x, y, z to 1, 0, and minus 1, it will be 0 and 2. Yeah, exactly is 0 and 1. So that means here is exactly 0 and 1. Okay. So now we find a map which puts every point in the curve to another space, right? And every point in this curve is well defined. Okay. So next we can find another point between side B to side A. It's just between from the P1 to x squared plus y squared is equal to z squared curve, and here. And yeah, how can we find a P to satisfy this equation? And we just put the symbol to the equation. So let's say we have s and t. We want to find a map and it satisfies this condition. We just let s is equal to ix plus z and y equals t, and we can solve the okay, wrong word. Below the equation and x, and we can get x some. We can. Here's the idea is we just represent x, y, z by s and t. So you can do it by yourself, and for saving time, I'm not show you step by step, but it's easy, and I will directly write here. Yeah, we can find another per se, but our per se is well defined on every point on this and these two things, and yeah, I would say it is, because if it map to all 0 point, it will be, I'll see here, it will be some equation. And we find the only solution of these equations is just this point is not exist in the projective space 1. So now we find a well-defined pi and a well-defined per se, okay, well-defined per se, and we apply. We can just check using the this map, and we'll find the equation is balanced. Okay. So all the things, what's the relationship between all these things and the circle star curve paper, the map in the circle star paper? I would say it's you just apply this rule, and again apply. I mean this rule. Okay. This rule. Okay. You find it. Okay. So yeah, you can check it by yourself. Okay. So I think that is the lemma in the paper don't speak too much, but I think it's the underlying thing of the lemma. Okay. Thank you. Mm-hmm.
So you find you map x, y, and z to the x plus z and y, right?
Yeah.
And
that's the point.
You keep going, so you can find 0, 0, right?
Yeah.
So what was the issue with here? So yeah. So if I define the point to 0 and 0.
Yes, you're right. We want to prove two sides is isomorphic, and the map between two sides should be well defined. It means any point in the first side can be mapped to a meaningful point of two sides.
Okay.
But there is nothing in the two sides, but yes, two sides. So any project space have 0 point. So yeah, it's that. So we can change the equation by apply some same component, and we can find another solution of this map. And
what's the final conclusion? So you have this, then you will finally get a circle curl, or?
Yeah, we just apply this. Okay, just write this one. And there are two maps between this one and this one in the paper, right? So well, from this one to this one, we can show T, right? So Y, we can apply these things and back to here, and we'll show we have as T in the parallel space, right? And here T is just T is equal to as divide T, right? Here the T in the paper is just this one, right? So yeah, here the T in the paper is just it depends on the description. In the paper, the T is the description of this paper we call P1 space is some T and plus a point in infinity. So T is just element in FP. So we can map this equation to the T and by S divide T. And we can apply the rule, okay? Here it is T. So we can apply the rule. Oh, okay. So yeah. Yeah, we should from this side to this side. I'm wrong, but yeah. 1z equals to 1, and the point in the curve is x, y, and 1, right? So we can apply this one to here, and we'll find z is equal to 1. So we can just put there to there, and we can get there. We will find x plus 1 and y. And there, this thing apply to this convention, and you see this is t and this is s. Oh, maybe I'm not thinking of t. But I think it's the same thing if you divide y by x plus 1. If it would be 1, y plus 1. It's a map in the paper. So you can check by yourself to apply the rule, and you'll find it's the same thing on the paper. Okay. Clear?
I don't think so.
Yeah.
So do you mean that you have analyzed this 0 point in projective space?
Yeah.
It will be easier to do in the finite space.
Yes. But because when I first read the lemma 1, I feel a lot of concepts, and it suddenly showed the map between a curve in the affine space and projective space itself, and it very confused me. So I just want to try to understand what the author meaning.
So what's the relationship with this?
No relationship. I think this is just try to make people understand without this whole things.
So one question.
So we need a discussion later. I have those in now.
Okay. Thank you, everyone.